Hi, good morning to one and all. I am K.V. Harish, Assistant Professor, Department of Civil Engineering, IIT Kanpur. You are watching MOO's lecture course on hydration, porosity and strength of cementitious material. Today we will see lecture 9, concrete mix proportioning strategies. The textbook or reference materials are shown. Primarily the concrete mixture proportioning is from Indian Standards 10262. And some mixed design strategies are stated in IS 456. Overview. Today we will deal with two topics, Indian standard method of concrete mixture proportioning and mixed design strategies. So, concrete mixture proportioning, the definition of concrete mixture proportioning from IS is as follows: determination of the proportion of concrete ingredients, that is cement, water, fine aggregate, coarse aggregate, etc., which would produce concrete possessing specific properties such as workability, strength and durability with maximum achievable economy. The ingredients used in concrete should meet certain physical and chemical requirements mentioned in the codes and should be tested for certain properties based on certain standard methods of testing. Concrete mixture proportioning can be done by several methods. Some of them are listed here. Indian standard method, which is given in IS 10262, Indian Road Congress IRC 44 method, American Concrete Institute, DOE or British method of mixed design, Road Note 4 or UK method, sometimes through trial mixtures and several other methods. Now, the relevant Indian standards for concrete mixture proportioning are as follows: IS 10626 merely for the guidelines in concrete mixture proportioning, IS 456 for specific guidelines related to plain and reinforced concrete, IS 1343 for specific guidelines related to prestressed concrete. Sometimes different nomenclatures are used to indicate concrete mix proportioning. Some of them are as follows: concrete mix proportioning can also be called as concrete mixture proportioning, concrete mix design, concrete mix proportioning, design of mixtures or proportioning of mixtures, or mixture proportioning for concrete. So, all these things refer to the same name, concrete mix proportioning. Some basic information on workability, strength and durability in addition to economy for concrete is provided in some tables in IS 456 specifications before proceeding with concrete mix proportioning. So, the table for workability from IS 456 is as follows. Here we have three columns. The first column indicates what is the placement condition for concrete. The second column indicates the degree of workability desired for that particular placement condition, and the third one indicates the workability measured in terms of slump. The unit is mm. Now, if you take the placing condition, there are totally 4 different groups of placing condition provided. In the first group you have blinding concrete. Usually blinding concrete indicates a small layer of concrete that is poured before you place any reinforcement. The second one within the first group is shallow sections, then pavements using pavers. So, for all these placement condition, the degree of workability required is described as very low. In the second group, you have mass concrete, lightly reinforced sections in slabs, beams, walls, columns, floors, hand placed pavements, canal lining, strip footings. For all these things, the degree of workability is low, and appropriate slump value is 25 to 75 mm. In the third group, we have heavily reinforced sections in slabs, beams, walls, columns, slip form, pumped concrete, etc. And the description for workability is medium, and the corresponding slump value is either 50 to 100 mm or 75 to 100 mm. In the fourth group, we have trench fill, in situ piling, tremie concrete, and for that the degree of workability could be either high or very high, and the corresponding slump values in mm or 100 to 150 mm. And remember that some extreme cases for very low degree of workability or very high degree of workability, separate instructions are given in clause 7.1.1 or 7.1.2, which can be read at a later stage. Now, the second important table, which gives more information about strength of concrete from IS 456, is shown here. Again, here you have three columns. One is the group of concrete that is designated, the second one is a grade of concrete, the third one is the specific compressive strength that we can expect from a 150 mm cube tested at 28 days, and the strength here is measured in Newton per mm square. In the first group, we have ordinary concrete referring to M10, M15 or M20. Remember that here 10, 15 and 20 refers to 10 Newton per mm square, 15 Newton per mm square and 20 Newton per mm square respectively. Likewise, you have standard concrete where the grade is designated as M25 and it goes until M55, and likewise the compressive strength here ranges from 25 Newton per mm square to 55 Newton per mm square. We also have high strength concrete designated between M60 to M80 and the strength ranging from 60 to 80 Newton per mm square. Remember that this is characteristic compressive strength of 150 mm cube at 28 days. The third table that we have in IS 456 is for durability considerations. Here you have 5 different environmental conditions: mild, moderate, severe, very severe and extreme, and each of the exposure conditions are explained in detail. So, if you take mild condition, the exposure condition is as follows: concrete surfaces protected against weather or aggressive conditions except those situated in coastal areas. Similarly, for moderate, you have about 5 exposure conditions: concrete surfaces sheltered from severe rain or freezing while wet, concrete exposed to condensation and rain, concrete continuously under water, concrete in contact or buried under non-aggressive soil or groundwater, concrete surfaces sheltered from saturated salt air in coastal areas. So, like this, you also have explanations for severe, very severe and extreme. So, before using any concrete, we should be very clear about what is the environmental exposure condition, and this is very important because some tables will include all these exposure conditions and assign different values and we will see that in the next slide. So, in this slide you will see the minimum cement content, maximum free water cement ratio and minimum grade of concrete that is specified from economy perspective, and this table is also from IS 456. So, in the left what you have is you have the different exposure conditions: mild, moderate, severe, very severe, extreme, and again you have two broad classifications. One is whether you have reinforcements in concrete or not. The first one is plain concrete where you do not have reinforcement, and second one you have reinforced concrete, and within plain concrete again you have three classifications. One is minimum cement content that you have to use, second one is maximum free water cement ratio, the third one is minimum grade of concrete. Likewise, reinforced concrete also you have same classifications. At this point of time, let us see only the minimum cement content, because minimum cement content is a important factor from economy standpoint. We will again revisit this table at a later stage. So, what you find is that under minimum cement content for mild exposure 220 is provided, moderate 240, and likewise for extreme it is 280. So, you see that the minimum cement content is increasing if the conditions are extreme, and likewise the same is true for reinforced concrete also, where the values are changing from 300 to 360. You will also notice that the minimum cement content that is used for reinforced concrete, all these values from 300 to 360 are much higher than the plain concrete values ranging from 220 to 280 for that particular exposure condition. As I mentioned, we will revisit this table at a later stage. Now, coming on to Indian standard method of concrete mix proportioning. So, the step by step procedure is provided. The first step is we have to see what are the datas that we have at the initial stage even before doing the mix design. The second one is we should target at a specified strength, and we should also understand what is the standard deviation for that particular concrete that we are designing. Third one is selection of mixture proportions, and finally doing trial mixtures to find out whether the obtained mixture proportion provides the desired strength and other properties. Now, step 1, data such as grade designation, type of cement, maximum nominal size of aggregate, minimum cement content, maximum water to cement ratio, workability for that application, exposure conditions as we saw in the previous tables, maximum temperature of concrete at the time of placement, method of transporting and placing, early age strength requirements, type of aggregate, maximum cement content, and whether an admixture shall or shall not be used, and also the type of admixture and condition of use. All these things have to be known even before doing concrete mixture proportioning. Now, the second step is broken down into few more parts. In the first part, we target at a particular compressive strength. So, FCK bar is equal to FCK plus 1.65 times S. FCK bar is the target mean compressive strength at 28 days in Newton per mm square. FCK is the characteristic compressive strength at 28 days in Newton per mm square, and S is the standard deviation. Now, there is a factor 1.65 refers to a constant indicating a confidence level of 95%. In many cases, we can also take 99%. Accordingly, this coefficient will change. Largely for concrete, we use a confidence level of 95%, and the constant referring to the 95% confidence level is 1.65. Now we have to determine S, which is the standard deviation. So we go to the next part within step 2. Number of test samples from the site should be approximately 30 numbers, and this is with a condition that the concrete is used for the first time. When changes in concrete mixture proportioning happening at site for any batch, the standard deviation for that batch shall be calculated and checked. When standard deviation values are not available, then one can use the table 1 of the code IS 456, but you may have to remember that at a later stage, if possible, actual standard deviation should be calculated by testing the desired number of samples. Now in the table, what is shown is the grade of concrete like M10, M15, M20, M25, M30 until M55, and for the 3 groups the standard deviation can be assumed as 3.5, 4 and 5. And remember that this table can be used only if you do not have the standard deviation values, or it is not possible to determine standard deviation values. The third step is again divided into several parts. Part A is selection of water to cement ratio. The relationship between water to cement ratio and strength should be established for the actual materials that are being used. In the absence of such data, water to cement ratio corresponding to the 28-day target strength may be selected from the established relationship if available. If it is not available, then the water to cement ratio given in table 5 of IS 456 may be used as a starting point, and this is based on durability consideration. If actual relationship is available, then the same shall be checked with the values provided in table 5 and the lowest may be adopted. So we are revisiting table 5 of IS 456. So what you find here is there is a maximum free water cement ratio that is mentioned for different exposure conditions ranging from 0.6 to 0.4 for plain concrete or 0.55 to 0.4 for reinforced concrete. So if we do not have actual information, then as a starting point we can choose these values, but remember that actual relationship have to be established between water cement ratio and strength, and later on it has to be checked with these values before proceeding further. In the second part, we have selection of water content, and this is primarily chosen from table 2 of IS 10262, and in this table what you find is the nominal maximum size of aggregate is provided 10, 20 and 40, and for the nominal maximum size of aggregate, suitable maximum water content is also provided. So in this case, for 10 mm nominal maximum size, 208 kg of water should be used, and for 20 mm nominal maximum size, 186 kg should be used, and likewise for 40 mm 165 should be used. Remember that the maximum water content here is expressed in kg, which is also equal to liters, same values in liters, because the specific gravity of water is 1. And this table is primarily for angular aggregates and for mixture that has slump between 25 to 50 mm. In the third part of step 3, we have calculation of cement content. Since we know the water to cement ratio and the water content, the cement content can be determined by dividing one from the other. The calculated cement content can be checked with the table 5 of IS 456 again for durability aspects, and the maximum cement content values within the two may be finally used for the concrete mixture design. In the fourth part of step 3, we have estimation of coarse aggregate proportion. Based on the nominal maximum size of aggregate and grading zone of fine aggregate, coarse aggregate proportion mentioned in table 3 shall be selected for general concrete applications. The values provided in the table is for water to cement ratio of 0.5, and the same may be adjusted suitably if other water cement ratio is used for application. For special cases where we need pumpable concretes, especially in areas where we have congested reinforcement, the values mentioned in table 3 shall be reduced by 10%. Similarly, IS 383 specification provides the use of combined coarse aggregate gradation, and if we prefer to use such gradations, then it shall be checked with the specifications of IS 383. And the table that we use in this step is from table 3 of IS 10262, and what you find here is the nominal maximum size of aggregate is shown in this column 10, 20 and 40, for which we have to choose the volume of coarse aggregate per unit volume of total aggregate for the different zones of sand specified. So, as we have already discussed in previous lectures, we have zone 1, zone 2, zone 3 and zone 4 for fine aggregates, and the volume of coarse aggregates per unit volume of total aggregate is chosen from this table. So, you may note the following while using this table. The volume of total aggregate is considered as 1 in this table. That is, if VCA is a volume of coarse aggregate and VFA is a volume of fine aggregate, VCA plus VFA is equal to 1, and hence VCA divided by VCA plus VFA is equal to VCA. What is this? This is actually the table values that are provided here, nothing but volume of coarse aggregate per unit volume of total aggregate. So that value will be equal to VCA again, because the denominator is 1. Now, the second note is, however, while using this table value for the calculation of VFA in the next step, VTA is not equal to 1, very important. So, in the next step, when we are calculating fine aggregate proportion, we have to make sure that VTA is not equal to 1. For this case, the value in the table will be equal to VCA divided by VCA plus VFA is equal to table value, or in other words, VCA plus VFA is equal to VCA divided by table value. This one we have to substitute in the next step to get the fine aggregate proportion. In the fifth part of step 3, estimation of fine aggregate proportion, the formula that is used is V equal to VCA plus VFA plus VC plus VW plus VCH, where here Ca represents coarse aggregate, Fa represents fine aggregate, C represents cement, W represent water, and CH represents chemical admixtures if they are used in concrete. And this volume is called as total absolute volume of concrete, and it is usually taken as 1. Now, VC, VW, VCH can be determined if we know the weight of cement, water and chemical admixture that are used, and if we know the specific gravity of cement, water and chemical admixture. So if we know all the specific gravity and the weights, we can find out the volume of cement, water and chemical admixture. Remember that we do not have the volume of VCA plus VFA, and for this we have to substitute the values that we got in the previous table. So substituting VCA plus VFA equal to VCA by table value in this equation above, VCA and VFA can be determined, weight percentage. So finally, step 4, once we arrive at the different volume proportions, we have to do trial mixtures. So what Indian standards suggest is, we have to do trial mixture 1 and check whether the workability that we targeted or we assumed have been obtained. Trial mixture number 2, if the workability is different from the originally targeted one, adjust water or admixture content suitably. Prepare trial mixture number 2 so that the free water to cement ratio is not much affected. Trial mix number 3 and 4, prepare trial mix number 3 and 4 so that the free water to cement ratio is plus 10% and minus 10% of the pre-selected water to cement ratios respectively. Sufficient information from trial 2, 3 and 4 are now obtained to conduct field trials. So this is approximately the procedure for the mixture proportioning of concrete. Now we go to the next topic, which is concrete mix design strategies. We will go through a brief introduction before getting into the strategies. For any application, concrete is usually viewed by engineers in 3 different angles, namely constructability, performance and economy. Remember that each one of them is given equal importance. Practicality and viability of using concrete or any idea or concept or technology for any application will not exist if even one of the above factor is omitted. Constructability may include factors such as workability, placeability and finishability, curing conditions and several other ideas or methods used for construction or placement. Performance includes primarily the property or properties that is required for that application. Performance may include workability, strength, toughness, modulus of elasticity, permeability, and remember that permeability will come as a durability factor, or any other methods in addition to the combination of the above property. So in some cases we may expect only one property, in some cases we expect combination of properties. Economy includes primarily cost benefits obtained either by using a particular concrete or composite or a method in comparison with the conventional ones. So both material and method plays a extremely important role in deciding the economical aspects. Understanding concrete mix design strategy will help to know how constructability, performance and economy can be varied or balanced for a given condition or situation. For every application, situations differs depending upon several factors mentioned previously. For some situations, multiple strategies exist, while for others only a few strategies exist. Identification of the most effective and feasible strategy is critically important for an engineer. Now, some of the strategies that we use for improving workability or water demand are as follows. Now, for improving workability, we can either increase the water content, we can decrease the cement content, we can decrease the cement fineness, we can increase the aggregate size, we can decrease the aggregate angularity or use rounded aggregates, increase the coarse to fine aggregate proportion, we can use water reducing admixture, and if possible we can reduce the ambient temperature. So you have so many strategies to improve workability, of which some are practicable, some are not practicable, because these strategies may affect other properties like strength and durability. So, in the case of increasing the water content, this is usually not preferred as it affects many properties, primarily strength and durability. So, what is usually done is fixing of the cement content by altering the aggregate content. So, this will usually result in high water to cement ratio. This is usually not preferred. The second one, decrease in cement content, can be done, but not lower than the minimum cement content required to fully coat all aggregates. So, one has to be very careful because a minimum cement content is required so that it can coat the surfaces of the aggregate and make sure that the mechanical interlocking in decrease in cement content, we have to make sure that we cannot lower the cement beyond or below the minimum that is specified. This is usually done by fixing water content and altering aggregate content. Thereby we can get high water to cement fineness. Decrease the fourth one, where we can increase the aggregate size, and this will result in 10% to 20% water reduction, and this is mentioned in table 2. In the fifth one, because of the use of rounded aggregates, one can get a water reduction of 0 to 15%, and this is also mentioned in table 2. Likewise, you have all other strategies, and when you use a water reducing admixture, you can result up to 5% to 20% water reduction, which is also mentioned in table 2. Now, the next one is some of the strategies that we use for improving strength. So, the commonly used strategies are decrease in water content. This is usually preferred provided it is economical and does not affect other properties. Fixing cement content by altering the aggregate content, and this will result in low water to cement ratio. Increase in cement content. So, here higher the cement content that can be increased should be higher than the minimum. The amount of cement content that you use should be higher than the minimum content required to fully coat all aggregates. This is similar to what we have seen in the previous case, and this is achieved by fixing water content and altering the aggregate content, and this will result in low water to cement ratio. The third one is decrease in aggregate size. The fourth one is use of angular cubical aggregates. The fifth one is use of water reducing admixtures. The following provides the strategies for improving permeability or durability. First one is decrease in water content. This is usually preferred provided the mixture is economical and workable. This can be done by fixing cement content and altering the aggregate content, which will result in low water to cement ratio. Increase in cement content, and this is preferred provided the mixture is economical and workable. This is done by fixing water content and altering the aggregate content, and this will also result in low water to cement ratio. The third one is use of supplementary cementing materials or mineral admixtures, and you also have other strategies. Strategies for improving economy, and remember, this is without compromising other properties or other performance. So, decreasing cement content, increase aggregate content, remember this is without affecting other properties. Optimizing aggregate gradation and size, optimizing the dosage of water reducing admixture, choice of source of aggregates. This will primarily reduce the transportation cost if the materials are locally available. You can also use other strategies to achieve economy. With this, we come to an end for this lecture. Thank you.